Okay, so we've got this new idea here, and I want to start showing you some stuff with basic quantum mechanics. And when I say basic quantum mechanics, I mean really difficult quantum mechanics. So let's start here with this idea. We have this idea of a matrix, okay? I've shown you matrices and linear algebra kind of things before, playing with it in Mathematica. And it's fun to look at, but what does it really do? Well, I'm going to set the stage for a quantum mechanics talk. Okay, I want to talk about this equation right here. This guy, it's called the Schrodinger equation, and what it really does is it works on, it takes this ht, multiplies it by this ket vector right here called psi t, sets it equal to a derivative of psi t multiplied by these constants. So, I mean, basically you just get waveforms out of it. But the better way to start thinking about this kind of thing is I've gotten these notes taken straight out of my notebook. I just wrote this stuff down. So I'm going to start talking to you about what it means. And we're not going to take long on this, so bear with me. It's just kind of looking at the kind of math that's used in quantum mechanics. Alright, so if you start to see these broad ket vectors, that's what they're called, broad ket, bracket, bra ket, bracket. You'll start to see what it all means. So welcome to a subset of drunk physics. I got me some wine here. We're going to have a good time. Alright. So, linear algebra for quantum mechanics. Alright. Now that sounds a lot more intimidating than it is. You have this idea called a complex number. Okay, it's this guy right here. I kind of wrote it in scratch writing. It's z equals a plus bi. And what is I? It's the imaginary operator. If you don't know, I don't know. It's like you learn about this in algebra when you're doing quadratic equations and stuff. I should assume that everybody knows what complex numbers are if they've graduated high school. So there's not really much to see here, except now you have this idea of a complex conjugate. So you take the a minus bi, carry all this down, and then when you multiply those two together, they always form real numbers. That's the neat thing about them. So you have this idea of ket vectors. That's what I was just saying. This psi ket right here, it's an array of complex numbers, okay? And when you multiply a ket vector by a bra vector, which is, set the other way, it's a complex conjugate is really what it is. It's you use these complex conjugates on each other and you multiply them in a matrix form. So the complex conjugate of this ket vector is a bra vector. I think I got that right. Either way, when you multiply all these together, you end up getting a bunch of different forms of things, okay? So multiplying a bra vector over here, so a bra with b ket is this form right here. So you take this guy right here, this bra form, a1, a2, a3, and then b1, b2, b3, and multiply them together. And what you get is kind of like a dot product with complex numbers, okay? Not really that difficult stuff to look at. Then you have this idea of linear operators. Okay, now linear operators are much more important in this grand scheme because they're matrices. Okay, so you get this alpha up here. This is the form a linear operator must take. It's going to be a matrix. It's going to be a square matrix, but it also has these nifty properties that we're not going to go into a lot of great detail about. But what it does is it acts on these bra or ket vectors in such a way that it gives either a row vector like this, so this almost like a dot product, you just kind of add them all together, or it gives you this column vector. Okay, so either way, it takes out a vector, multiplies it by itself, this alpha times b, b ket, and it spits out another vector. So this whole thing is going to be one number. So this first row here, alpha 1, beta 1 plus alpha 1, 2, beta 2, etc., etc. it's going to spit out one number. So you're going to have a new column matrix, or a new column vector with some numbers, okay, and they're going to be elements of the complex plane, right? Not difficult stuff. Then you get this compound product. You multiply a bra by a linear operator, and then you multiply it by a ket vector, so you get the bra here. Then you get the linear operator here, and then you get the ket vector, and you multiply it all out, and it becomes this interesting new thing. Okay, then you have the inverse. Now, there's just all kinds of rules. It's kind of what I'm getting at here. This compound, I'm going to scroll down here because this is where it stops. So you multiply all of this stuff together, and this gives you rules for doing matrix algebra with complex numbers, where all of your values in your square matrices and your vectors are going to be complex numbers. It just teaches you how to do them. And your complex conjugates, when you, like I said before, when you have complex conjugates here, right, you have this bra vector denoted with a you set them together, and what they do is they kind of make a dot product with each other. Multiply this by its complex conjugates. There's a bunch of stuff, but the main rule here is that matrices made with complex numbers obey the rules, both matrix algebra and complex algebra, with some extra rules to make the two objects work together. Okay, so I said we weren't going to spend a lot of time on this, but it just kind of gives you a look at the kinds of things you're going to be seeing when you do, you know, computational quantum mechanics, the field I'm most interested in. I could show you a whole notebook filled up with notes on this stuff, but it's pretty easy once you kind of get the hang of what you're looking at, because it's all just a bunch of squiggles. So you see all this noise, and you have no idea what it really means. But then you see this this time-ordered ket vector, which means that you're going to have a stack of functions in time. And then you take your derivative with respect to time of those functions with time. So you're going to have ft, you know, gt, ht, you know, 3 different time functions stacked up in a vector. And then you're going to multiply it by this object here on the first side, which is a linear operator. And this can be stacked up any sort of way you like. There's a lot of different ways to write quantum mechanics and do math with quantum mechanics, but all it is, well, at least in matrix mechanics, that's how it really kind of first got formulated, is by noting the fact that you can do operations with matrices and make it look like quantum math. Because it's like coin flips, it's discrete operation.